So function notation, remember this idea of a function where one input has exactly one output. We have a way that we write functions to kind of represent that input and output. So our two goals for today's lesson are our learning targets. We can use function notation to evaluate and interpret functions. Evaluate just means get a number out. And then we'll do a little bit today of function notation to solve and graph functions. That won't be our main focus, but we'll do at least one example. So here's kind of our definition box. So linear functions can be written in the form y equals mx plus b. We had that the last 2 days. That's your slope-intercept form, where x is your input, y is your output. We said yesterday with the KFC bucket that b was your starting value and m was your rate of change. But we can also name a function with this function notation where we replace this y with a f parentheses x. It's right there. That's what the function notation is. We call that f of x, and that's just the notation that we use to represent a function. It means the same thing as just having y there, but as you'll see as we go more through this unit, that writing this in this specific notation, f of x, has some advantages. So, and that's kind of the point I was trying to get across in the second bullet point, that the notation f parentheses x, and we say this if you're trying to put it into like English, we say f of x, and I would have all of you guys write that down. F of x. Again, that just can be in place of our y. F of x is just kind of another way we can express what our output is going to be. So if f is a function, and we just use f as kind of the standard because function starts with f, but we could really plug any letter in there. We could have g of x, we could have h of x, we could have m of x, but the one we start out with is just f for function. If f is a function and x is an input, then f of x represents the output corresponding to the input. That's a lot of words. We're going to draw kind of a little diagram or picture to help us do this. So somewhere in kind of your definition box, write a big f of x. And then this x here, I want you to draw kind of just an arrow to the x and say this x that you're plugging in, this represents your input. And then if you take the whole thing together, so with that f and of the x, so you go from all of that, that represents what your output's going to be. So if where you'll see in the next few examples, this x is going to be replaced with numbers. So if this was a 1, that means we're inputting a 1 into our function rule and we're evaluating, and we'll get a number out, and that will be our f of x number or our output. So, scooch over to example 1. So we're trying to evaluate the function, and our function is f of x equals x plus 3. So this is the function that we're dealing with. And we're specifically asking for it when our input is -4. So here, -4 is going to be our input. And what that really means is we're going to plug in -4 for x. And this was part of the Desmos activity that you all did last week, some of this function notation. So I'm going to write it. You write it as now we replace this f of x up here. We just say now it's f of -4. And now instead of writing that f in there, since -4 is our input, and this is our input too, this x value, we're going to substitute in a -4 for x. -4 plus 3. I'm actually going to change this. I'm going to try to keep it color coordinated so you know what we're talking about. And now on the right-hand side of our equal sign, we're just going to evaluate, which means combine like terms, multiply, do whatever you can. So we're just taking -4 plus 3. So that would be -1. And we could write our final answer as f of -4 is equal to -1. So this is our output. When you hit, in this function rule, on this function vending machine, when you hit -4, it's going to spit out a -1. And how we're going to express our answers as points. So we're going to write our final answers as -4, comma, -1. Or again, this is our x value, this is our y value, and this is our input, and this is our output. So to summarize, whatever is replacing this x inside the parentheses, that's what you're plugging into your equation, and you're just getting out another number. The other number you get out is your output of the function. We'll try this second example. We're evaluating now -4x plus 7 when f with f of 2. So again, 2 would be our input. That's what we're plugging in for x. So we can say plug 2 in for x. Again, it may seem silly to like write down the steps. That's a good initial way to kind of start putting those steps to memory almost. Writing it down a few times, so when you see a problem like this, hopefully your brain goes back to, okay, I know at least where to start. So we would say f of, then we replace, wherever we see an x, we replace it with the positive 2. And we're also going to plug it in for that x in our function. So -4. I'm going to substitute in with the -2. And again, after we plug it in, we have to evaluate. That's evaluating the right-hand side. So we can take -4 times -2 and get a positive 8, because a negative times a negative is a positive. Yeah. Oh, sorry, let's do a positive 2. Good catch. Positive 2. So it should be a -8. And then we add 7. Yeah, it'll be -1 again. So if we write this as a ordered pair or a point, we would say 2, comma, -1, where 2 is our x, -1 is our y, or You remember y is the same thing as your f of x. It's almost better to write in this context f of x. These two things mean the same thing though. F of x and y, they both represent outputs. And x's are always going to be our inputs. All right. So that's one piece of function notation. This is kind of the way when we know what our input is, but we don't know what our output is and we're trying to solve. Not solve, I just say evaluate. Our next example, you'll see it looks a little different. It says solve for x this time. Now we don't know what x is. We have a function, f of x is equal to 6x plus 9. And we need to find the value of x for which f of x is equal to 2. So what this is saying, and we want to put this into words, find the x value that makes the output 2. 21. I had that part cut off. So, notice how now we have this f of x set equal to 21. This is already telling us that f of x, if f of x stands for our output, this is saying that our output is equal to 21. And what we can do in this case is just substitute in or plug in 21 for f of x. So taking the original function I have, I'm replacing this f of x here with 21. So I'm going to write 21 is equal to 6x plus 9. Now this is an equation that we can solve for x. So whenever you're giving an output and it's asking you to find the input, it's just solving an equation. When you're given the input, it's evaluating the difference between the two. So we go through and we do some subtracting. We'd have to subtract 9 from both sides as our first step. So then when we do that, this will be 12 is equal to 6x. And then we would have to divide each side by 6 to get x by itself. So x is going to be equal to 2, or 2 is equal to x. Again, we're going to write this as an ordered pair or a point for our final answer. So in this case, now we found our 2, and our output was 21. So this is our x, this is our f of x, 2 is our input, f of x is our output. And we could do it in reverse to check our work to see that this is true. If I plug 2 into my original, I'd take 6 times 2, which is 12. Then I would add 9 to it, so I'd get 21. So I know 2 has to be the right answer. I hit 2 on my vending machine, I get out a 21. Think about, in this example, you started with your output. So it's like you go up to a vending machine. You didn't buy anything, but you're going up to it. And there's already a Snickers bar waiting for you. And then you can infer, based on seeing what's in the vending machine, what button the person pressed to get out that Snickers bar. All right. Kind of the last piece of function notation is just kind of putting these two ideas together if you're given a table. It says we want to graph the linear functions, and it starts off with a table and some blanks in that table, and we're going to fill in the blanks. So whenever you're giving an input, this is the easier one, I think. You just have to plug whatever it is for x, plug it into your original, and then you get your output. So for an input of -2, I would say f of -2 is equal to 2 times -2 plus 5, and then I just evaluate. So I take 2 times -2, which is -4, and then I add 5 to it, so I get out a +1. So that will be my output, +1. If I do the same thing with f of -1, we get -2 plus 5, which would be a +3. And I know these are easy enough to do in your head. Like, yes, you could multiply 2 times -1, then add 5 in your head. But it's worth, when things get longer, it's worth practicing using this notation to keep all your pieces together. All right. Our next row in our table, we switch now. We're given an output of 5, but our input, we do not know. So this goes back to that last example we did just above it, where we're going to set now our equation or our function equal to 5 and solve. So 5, this is our f of x. F of x is equal to 5. That's what our output is. So if we solve this in 2 steps, we could subtract 5 from both sides. We'd have 0 is equal to 2x. And then we'd have to divide each side by 2. So x would have to be 0. So again, since it's an x equals 0, we know that's an input. 2 times 1 is 2. Adding 5 to it is 7. So we would get 7 here. I was going to have you graph this. If you were to graph it, we actually should, because I think you have to do it on the back side. Just remember, this is your x values. These are your y values. All of these are points. So what we made in our table. So this would be like -2, 1. This is -1, 3. 0, 5, 1, 7. So we go over 2, down 1. Sorry, over 2, up 1. It's +1. That's -2, 1. We go over 1, then we have to go up 2 more. So that's -1, 3. We're at 0, 5, so that's right here. And 1, 7 is up here. You can see this is linear, and it's a function. If I do my vertical line test, anywhere I draw a vertical line, it'll only cross my graph once. And it goes up in a straight non-vertical line, so I know it's a linear function.